What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and zero defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amsted Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of Galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, humanity mines nearly 2.5 billion tons of iron ore worldwide. That's over 5 trillion pounds of metal, without which we wouldn't have skyscrapers, roads, or even your smartphone. Iron drives civilization, but few people know where it truly comes from. Because every piece of this metal isn't just ore from a quarry, it's actually a fragment of an ancient star's explosion. And today, you're going to learn something most people don't even suspect. Stick around till the end. There's a hidden answer there that will completely change how you think about iron. The global iron production is an incredibly massive process that drives industrial development and shapes the modern world. Every year, the world extracts nearly 2.5 billion tons of iron ore, or more than 5 trillion pounds. This ore is the primary raw material for steel, without which we couldn't imagine building skyscrapers, cars, bridges, or even modern machinery. The leading iron ore producers are China, Australia, and Brazil. Australia, for example, mines more than 900 million tons per year, which is roughly 2 trillion pounds, making it the world's largest ore exporter. China, while producing significant amounts of its own ore, is also its biggest consumer, using nearly 1,200 million tons annually for steel production. Iron ore mining involves massive quarries, where giant trucks haul hundreds of tons of ore in a single trip. For example, one modern Australian mining truck can carry over 400 tons of ore at once. That's equivalent to the weight of more than 270 average cars. The global iron industry keeps pushing forward. Thanks to innovations in extraction technology and reduced energy consumption, production is becoming more efficient and environmentally friendly. Take the United States, for instance. They're implementing new systems to cut carbon emissions in steelmaking, gradually transforming traditional approaches to the industry. Iron demand is skyrocketing worldwide, especially in developing nations where they're building roads, railways, and massive infrastructure projects at breakneck speed. Simply put, iron is the real engine driving global development, and its production is a powerful indicator of economic strength. The iron we pull from the Earth's crust has cosmic origins. It was formed in the distant past, long before our planet even existed. Most of the iron in the universe was born in the hearts of ancient stars through processes called nuclear fusion. When a massive star reached the end of its life cycle, it exploded as a supernova, blasting heavy elements, including iron, out into space. This cosmic dust and gas gradually came together over time, forming molecular clouds that eventually compressed into protoplanetary disks. Earth's iron is what remains of these ancient stellar explosions, preserved and woven into the very fabric of our planet. That's why iron is one of the most abundant metals on Earth. During Earth's formation, over 4.5 billion years ago, the early planet was molten due to intense gravitational compression and frequent meteorite impacts. During this period, heavier elements, including iron, sank towards the center, forming the planet's core. Today, it makes up roughly 1/3 of Earth's total mass, and that's exactly why our planet has its unique magnetic field. The iron core powers this protective shield. Iron in the upper layers of the planet forms mainly as iron ore, a mixture containing oxides and other iron compounds. It's distributed throughout Earth's crust and mantle, and that's where we extract it from to create metal for every aspect of our lives. From iron's origins in stars to its crucial role in shaping our planet, this metal has traveled an incredible journey before becoming part of buildings, machines, and even your smartphone. So every piece of iron in the world is essentially a cosmic artifact, carrying within it the history of the universe and our planet's shared story. Iron almost never occurs in pure form in Earth's crust. It's hidden within numerous minerals, oxides, sulfides, silicates, carbonates, and other compounds. The most common iron minerals are hematite, magnetite, siderite, limonite, and pyrite. The iron content in these ores ranges from 10 to 70% or more, depending on the type and quality of the ore. To get metallic iron, you need a pretty aggressive and complex technological approach. In industry, the main method is the blast furnace process, where iron ore gets heated in a blast furnace at extremely high temperatures, around 2,900 degrees Fahrenheit. There, under the action of coal and other additives, the ore is reduced, meaning oxygen is separated from the iron, and molten metallic iron forms, which collects at the bottom of the furnace. Other methods, like direct reduction of iron, are used to extract metal from finer concentrates in the form of iron powder or sponge iron, which can then be remelted. So, iron gets freed from minerals through engineering processes that demand extreme temperatures and chemical reactions. This aggressive approach is what transforms the iron buried in ores into strong metal, the foundation of modern civilization. The molten metal pools at the bottom of the furnace, separating from the slag, impurities that float to the surface. Pig iron typically contains 3 to 5% carbon and other impurities, so it needs further processing. The next stage is the converter process. Here, molten pig iron from the blast furnace gets transported to an oxygen converter, where a jet of oxygen further oxidizes excess impurities and carbon. The result is steel with controlled carbon content, maximum 2%, depending on the steel grade. The molten steel then moves to the casting lines. This is where slabs are formed. Massive flat ingots ranging from about 6 to 12 inches thick and up to several feet wide. A single slab can weigh dozens of tons. These slabs are an intermediate product that's then sent to rolling mills, where they're transformed into flat sheets, strips, or other profiles for future use in manufacturing structures, automobiles, construction rebar, and many other products. It's important to note that this entire technological chain requires high energy intensity and precise control of parameters: temperature, chemical composition, and processing time. Engineers control the process with high precision to achieve the necessary steel quality, strength, and durability. Besides traditional blast furnace production and converter refining, modern metallurgy increasingly uses electric arc furnaces, where steel scrap is remelted with molten iron, added to save resources and reduce environmental impact. The process starts with loading steel scrap into the furnace, pieces of metal, production waste, or old metal products. To improve steel quality and optimize melting, iron particles or iron concentrates are sometimes added to the scrap metal. After loading, the electrodes lower until they make contact with or get close to the scrap, and current flows through them. An electric arc forms between the electrodes and the charge, reaching temperatures up to 6,300 degrees Fahrenheit. Heating the charge under the arc's influence causes the scrap metal to melt rapidly. The molten steel forms a pool of liquid metal that mixes intensively thanks to electrodynamic vibrations and natural convection. This ensures uniform heating and metal composition. To purify the molten steel from unwanted impurities, oxygen is introduced into the furnace through special tuyeres. The oxygen oxidizes carbon, sulfur, phosphorus, and other harmful elements, forming slag that's easily removed. Alongside this, fluxes are added, materials that help neutralize impurities, improve slag formation, and protect the metal from air exposure. Refining continues until the desired chemical composition is achieved. When the metal reaches the required quality and temperature, it's poured from the electric arc furnace into special ladles, containers for transporting liquid steel to the next processing stages. On continuous casting lines, the molten metal is transformed into slabs. The weight of a single slab can reach anywhere from 20 to 30 tons. These billets serve as the foundation for further rolling into sheets, bars, pipes, and other metal products. The main advantage of electric arc furnaces is that they can run almost entirely on scrap metal, which dramatically cuts down the need for mining iron ore and slashes energy consumption. This makes steel production way more eco-friendly and cost-effective. The furnace is constantly monitored by operators who adjust the current strength, voltage, and oxygen flow to optimize melting and hit the exact steel specs needed. Graphite electrodes wear down over time from the extreme heat and need to be replaced regularly. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, It's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site. Concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed, foundation, dam wall, turbines, and generators, comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, They use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born, not just to build, but to preserve. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside, for example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads.